Hi folks, welcome back to our discussion on forces. We've gone through the basic types of problems. We've gone through the three Newton's laws. We're now going to continue into talking about connected masses and inclined planes as well as elevators. Okay, so today we're going to talk about this tension. Okay, tension occurs within a material that is being either pulled or stretched. Okay, so anytime we've got some type of material that's being pulled or stretched, we're going to talk about this tension. Okay, now it is an internal force that acts at all points along a rope, string, or chain, and it acts in both directions. Okay, so it acts in both directions along that rope, chain, etc. Okay? So, what is this tension? Okay, essentially it's something being pulled at both ends, right? And everywhere along here, because they are connected, it's pulling in each direction at the same time, right? So every point along here is connected, and if I pull on one side, I'm actually pulling on all of the pieces, right? So if this is attached, I'm pulling at all sides. If I have too much force on either end, I break whatever I'm doing, okay? But up until that point, we're talking about this idea of this tension, okay? An internal force that happens along all points along a rope or a string, and it's going in both directions. All right, let's take a look at our first example that we're here to understand a little bit about this tension. All right, so we've got two carts attached by a rope being pulled along a flat surface. Okay, and we're going to assume frictionless, or friction is negligible. We're going to ignore friction for this time being. Okay, so if I'm pulling it in this direction, this is my F applied, okay, my FA, right? And we are told that we are pulling this M1 force this M1, this mass, with an applied force of 40 newtons. Okay. Well, one thing we want to consider here as well as we do this is we want to draw in all of our different forces that are on here. So we can do this as a free body diagram as a connected free body diagram. Okay. Well, on this mass, we're going to call this FG1. Right, we're at mass 1, we're going to have that force of gravity pulling it down. We also have this FG2 over here. Mass 2 has that gravity pulling it down. Well, we're on a flat horizontal surface, so if I've got my gravity pulling it down here, I also have my normal force, my Fn1, up here, and similarly over here I have my Fn2. Okay, we're ignoring friction in this, we're saying frictionless, otherwise if we're applying it that way, friction would be pulling in this direction. But we're now talking about tension, we've got to draw that in here, okay? Because of this rope, this mass is being pulled this way by tension, okay? And since this rope is attached to this M1 mass, tension is also pulling it back in this direction as well, right? We said tension goes in both directions. If I'm pulling on this side here, right, this mass here is pulling this way, so we see this mass being pulled, but this mass is also pulling this one back, and we see this tension going in both directions, okay? Let's take a look at this and say, well, what is our F net for this entire situation? Okay, well, our verticals we're not really too worried about because we're on that flat surface. Our FG1 is the same as our Fn1, our FG2 is the same as our Fn2, right? Force of gravity equals the normal force when we're on that flat surface. So if I'm looking at my F net here, I am looking at, I have my F applied, right? We're pulling it in this direction, okay? Minus my tension that's on this piece, and then I have my tension in the opposite direction here, so plus tension going the other direction. right? Equal and opposite, right? And so when we're looking at these, what actually happens is we've got this negative t and this positive t, they just cancel each other out. And so when we're looking at this, all we have now is our F net is equal to our F applied, which is also equal to our mass times acceleration. And if we were only dealing with this one, then that makes sense, right? This is what we've dealt with before. We have our mass and we have the acceleration. But we've got this coupled system, right? They are together. So we need to talk about the total mass of the system. Okay? So the question for this one was, if this has an applied force of 40 newtons, what is the acceleration of the carts? All right, well, looking at part A, we want to know that if our F net is equal to our F applied, and our F applied is equal to that mass, the total mass times acceleration, well then acceleration is just going to be that applied force divided by the total mass. So we have our 40 newtons divided by our 10 kilos, and this gives us 4.00 meters per second squared for our acceleration. Okay, very similar to what we're doing in the past. However, this time we've got to talk about the total mass because we have this coupled system. Okay, and we've got a note in here. Note that tension, okay, cancels out of the total F net equation. Okay, so we've got that right here, right? Tension cancels out of F net, right? They're in equal and opposite directions, so they cancel each other out. Okay, so that was part A. If we have a coupled system, how do we calculate their acceleration? Okay, next up though, part B of this wants to know what is the actual tension that's involved in this situation. Okay, now we can do this in both ways. We can look at our M2 or our M1 situation. Okay, so let's look at this M2 situation. Okay, if we're looking at our F net here, okay, F net, well, the only force that's acting on this one is that tension, the tension pulling it away from here. And since we're talking about this M2, this is going to be the mass, or F net is mass times acceleration, but we're only dealing with this mass too. Now we had an overall acceleration from the previous calculation here that I'm going to include into here. And so our entire system, because it is connected, is accelerating at this 4 meters per second squared. So we know our mass from the information provided us in the problem. We know our acceleration from the first calculation. So when we go to find our tension, it's going to be that 6.0 kilograms multiplied by our 4.00 meters per second squared, or we get tension at 24 newtons. Okay. Now we can also take a look over here at M1 and figure out our tension from M1. Okay, so we're looking over here at M1. Again, we're looking at our F net. Okay, now this is going to be that M1A, right? The acceleration of the system on this M1. Okay. But what is that equal to here? This is also going to be our F applied minus our tension. Because if we're looking at just this one mass, we have the applied force going to the right, we have our tension going back to the left, and then our vertical Fg and Fn cancel each other out. So we are looking at this situation. Okay, well, I'm trying to solve for tension. I have the mass, I have my acceleration, and I have my F applied. So if I'm looking to solve for my tension, it is going to be bring it to this side, bring that to their side, we get our F applied minus M1A. And now it's just a matter of plugging in our values. We have 40 newtons for our applied force, minus we have a mass of 4 multiplied by an acceleration of 4. So we have 40 minus 16, we get 24 newtons. Okay, so we solved for the acceleration of the system by treating this as one whole piece, right? And then once we know that acceleration, we can start to calculate that tension based on the acceleration of each individual block and the applied force. And in our notes there, we said that it's the same in both directions, and just doing those individual calculations, we prove that it is the same in both. Okay. A couple notes here. We say since it cancels out of the total F net equation, we only consider the forces acting on one mass when we're trying to figure out the tension. And since tension acts on both masses equally, we can use either mass to solve that tension, as we did here in this example. Okay, I will work through a couple more examples here, but first I just want to talk about how to draw a free body diagram for these types of situations. Okay, so we did that one on that horizontal, but if we consider two masses hanging from a pulley. Okay, let's just call this M1, M2. Okay. Well, let's see, what do we got here? For M1, we have force of gravity pulling it down. Okay, and since it's attached to this rope, then that means that we have our tension pulling this one up. Okay, that's the only two forces acting on this M1. And when we look at M2, we see something similar. We have this force of gravity pulling it down, so Fg2, and then this mass is being held up by this rope, so we have tension going in that direction. Okay. And when we have a situation like this, as it says here, sometimes it's easier to turn this into a horizontal situation. And so if I did that, we have our M1 connected to our M2, okay? And so if we notice where the rope is here, that means that I have from M1, I have my tension going in this direction, and from M2, I have tension going in this direction, which means then that we would have had our Fg1 pulling in that direction and our Fg2 pulling in that direction. Okay. Now I have said that part of this is we want to make sure that we draw free body diagrams for most of these problems, right? We want to be able to draw these out because it helps us to be able to calculate what is our F net. We can look at the different setup and try to calculate all these different components of that F net. I'm not concerned which way you draw your free body diagram. I would accept either the way that we have it here where it's on the pulley, or if you spread it out. Just be careful of how you set it up and how you draw that free body diagram. Hopefully over our next couple examples we see me using those and help to understand a little bit better. All right, let's get working on our first of 3 examples that we have here. The first one we're going to deal with is this pulleyed system again. Okay, we have 2 masses hanging from a pulley, a 6 kilogram and a 4 kilogram. We start from rest, we let go, we want to know what happens. So first off, we want to find out is what is the acceleration of the system, and then we want to calculate the tension in the string. Okay, so first off, let's draw our free body diagram. We have Fg1, and here we have Fg2. Right, gravity is pulling both those down, and then for both of these situations, we also have that tension pulling upwards. Okay. Now I've also said we can draw this horizontally. Like so, where we would have, once again, tension in those two directions. We would have FG2 and FG1. Okay? Now, the reason why this unfolded version might be helpful is because we're looking at FG being pulled in that way and FG1 being in this way. So it's kind of like if we're having a tug of war, right? We've got one person pulling horizontally that way, one person pulling horizontally this way, and we're not worried about any of the vertical motion in the way we've drawn it here. Here we're only dealing with the vertical, and sometimes this can be a little bit harder to understand which way is going to win out. So I'm just going to draw these both ways, and I'm going to fill the work underneath here, but understand that it would be the same as if I filled it out on this side here. Okay. Looking at this one piece here, okay, the way we've got this drawn out, we can say that F net equals I'm going to say I've got my FG1, okay, tension is going the opposite direction, so I can say minus tension. Then I look over here, I've got plus tension, and then I've got my FG going in that direction. So I guess I should state first that this direction I'm calling positive, and that direction I'm calling negative. Just because the way that I've drawn it out, I'm going to stick with one first. So this direction is positive FG1, and then I've got this tension as a negative tension. I've got a tension going in this direction, which I've said is positive, and then I've got my minus FG2. And we've said that these are the same, so they cancel out. And so when I'm looking at this, my F net is just then my FG1 minus my FG2. Okay. Well, FG1 equals M1G. Okay. So we end up with 6 kilograms times gravity, and I get 58.8 newtons. Okay. Switch colors here for FG2. This is M2G, which is going to equal 39.2 newtons. All right. Now this question was wanting to know what the acceleration was. Well, F net, we broke down those individual forces, but we want to remember what F net is. F net is just that total mass times acceleration. Okay? So I have an FG1, I have an FG2, I have my total mass being 10 kilograms, so I can solve for my acceleration. In this situation, acceleration is FG1 minus FG2 divided by my total mass. Okay, 58.8 minus 39.2 divided by my 10 kilograms for my total. This gives me a 1.96 meters per second squared. Now, I purposely set it up so that we have a positive value, so that means it's going in this direction, which if I look here, that means that our whole system is going to accelerate downwards, or this FG1 is going to accelerate downwards at 1.96. This piece here would accelerate upwards at that 1.96 meters per second squared. Okay? So that helps us understand the situation, and hopefully we realize that if we had a 6 kilogram mass and a 4 kilogram mass on here, we let them go. The 6 would go down, the 4 would go up. Okay? All right. So we've solved that. Let's type or put that into this piece here. And now let's take a look at solving for the tension of this system. Okay, If we are looking at M1, F net equals FG1 minus tension. Okay? And we know that since we're talking F net, this is M1 times A, because we're only talking about that individual mass, not the total system. So we can then say tension is equal to Fg1 minus M1A. We calculated this Fg1 in the previous section there to be 58.8 newtons, okay, minus our 6 kilograms times our 1.96 meters per second squared. This gives me a tension of 47 newtons. Okay, now that was solving from M1. Okay, now I said they're equal and opposite. Let's go back and see how this works and see if we get the same answer for M2. Okay, so for M2, we are looking at F net is equal to. Now, we know this is accelerating upwards because we found that the M1 is going to go down, M2 is going to go up. So that means that we're going to take our tension minus Fg2. So if I rearrange, and that is equal, F net again is M2 times A. And so if I want to rearrange this, I can say that tension is then going to be M2A plus Fg2. And so we get our 4 kilograms times our 1.96 plus our Fg that we had calculated out previously to be 39.2. And this also gives me 47 newtons. All right, so when it comes to tension, choose a mass. It doesn't really matter, okay? The key notes on this one is when we're solving for acceleration of the whole system, we need to consider the total mass, right? Because we want to talk about how the whole system is accelerating. When we want to find tension, we only need to use one of the masses. Using both to calculate to verify is totally up to you. However, we only really need to do one mass, and that's what I'm going to continue with moving forward, is figuring out just the tension on the rope using one of the two masses. All right, let's move on to example 2. Okay, our second example. We have this mass on a frictionless table, okay, is attached to this hanging mess over a frictionless pulley. Okay, so we're just going to kind of deal with this frictionless version of this one first, and then we will get into a system with friction in the second or the third and final example. Okay, so as drawn here, and I've listed my M1 as my 6 kilograms and my F2 or my M2 is my 8 kilograms. All right, so what do we have here? Well, let's draw our free body diagram on here, and then we'll lay it out horizontally and draw it that way as well. So I have Fg1 acting on this mass, and I have an Fg2 acting on this mass. I have tension going up the rope here, and I have tension coming out of the rope that way, or out of the block, sorry, going that direction, right? Because this rope is attached here. And then since this is sitting on the table, I also have to have an Fn2, a normal force on this block as well. Okay, it's important to draw all of our pieces. Now, if I want to stretch this out, we have M2 connected to M1. And so over here, I still got my Fg2 pulling it down. I have my Fn2 going upwards. I have my tension going in this direction. Where the rope is attached, I have tension going in the opposite direction, and then I have my FG1 going in this direction. Okay, so for this example, it is a little bit easier to understand what forces we need for our Fnet from this unfolded version. Okay, so if I'm looking at this, my FG2 and my FN2, those are going to cancel each other out, equal in opposite directions. So I'm looking at my Fnet is then equal to, and I will say that this direction is positive. So I see my FG1, I have tension going in the opposite direction, so minus tension, and then I have this tension going in that direction, so plus tension, and again, this is equal to my total mass times acceleration, because that's what my Fnet is. Okay, and equal in opposite directions on my tension, so those cancel out. So when I go to figure out my acceleration here, I'm really looking at Fg1 is equal to m total times acceleration. Or acceleration is Fg1 divided by my total mass, and my Fg1 is m1 g divided by my total mass. Okay. So all I gotta do is plug in my numbers here. I have 6 kilograms times by my gravity divided by my total mass of 14, and I get an acceleration on the system of 4.2 meters per second squared. Okay, 4.2 meters per second squared. Okay. So that is our overall acceleration on the system. That was the first part that we needed to solve. The second one is we need to find the tension. Okay, so let's write in there acceleration 4.2. Sorry, I ran out of room to not put the units on there. Okay, now we need to figure out our tension. Again, we can look at either one of the masses here to solve this. However, if I look at my M2, okay, if I'm looking at M2, my F net on this entire thing is equal to my tension, because that's the only horizontal force. The verticals cancel each other out. And that is equal to my F net for this piece here is just my M2 times A. Well, I just calculated my acceleration and I have my mass from the problem, so I can say that tension is just going to be that 8 kilograms times the 4.2 newtons to give us a value of 34 newtons. Sorry, 8 kilograms times 4.2 meters per second squared gives us our 34 newtons. We could also look at this situation here and say that for M1, our F net is going to equal our Fg1 minus our tension, and that will equal our M1 times A. Rearranging and solving for tension, you will also get that 34 newtons. Okay, so that takes us to the end of our frictionless table example. So I'm just going to get rid of this piece that we just solved. For our next example, we're going to use the exact same system, okay, where we have our 8 kilogram mass sitting on the table, we have our 6 kilogram mass sliding down, but what's different here is we now have a force of friction that is equal to 25 newtons, okay? There's no friction happening on this one. Our friction is happening on mass 2, and since this would slide this way, our force of friction is opposing that motion, so I'm going to put that right here. Their force of friction is opposing the motion involved in this overall situation. And again, we want to find acceleration and we want to find our tension as the problem for this situation. Okay. Well, once again, we're going to go back to our F net for the system. Okay. Again, we're going to go with this direction is positive. Okay, so we're going to say we have Fg1 minus tension plus tension minus our force of friction. And again, this is equal to the m total times acceleration, and tensions cancel each other out. So when we look at this to solve for, since this part disappears, this tension part disappears, right? They just cancel each other out. My Fg1 minus my force of friction, so force of gravity on that first block minus the force of friction equals the total mass times acceleration. So acceleration is then Fg1 minus force of friction divided by the total mass. All right, well, force of friction we were given in the problem is 25 newtons. Our total mass is 14 kilograms, and our Fg1 is our m1 times g, which is a value of 58.8 newtons, as we've solved previously. So plugging those values in here, 58.8 minus 25 divided by 14, I get 2.4 meters per second squared. Okay. 2.414 to be precise. But so we have that value, so let's write that in up here. Our acceleration was 2.4 meters per second squared. Okay, solving for the tension. Well, let's look at mass 2 again. And again, it doesn't really matter, mass 1, mass 2, it's entirely up to you. Okay, for mass 2, we're looking at our F net. Okay, in this case, we have tension, and then we've got our force of friction going in the opposite direction. And we know that this F net is m2 times the acceleration of the system. So solving for tension, this is then going to be m2 times a plus that force of friction. Well, mass 2 was 8 kilograms. Our acceleration is 2.4. And the force of friction we're going to add to that is 25 newtons. So 8 kilograms times 2.4 plus our 25 newtons gives us a total of 44 newtons on the tension. Okay? So when we compare this to that previous example, without any friction, we had our tension equal to 34 newtons. Once we have friction into our system, we cannot just take that unfriction system and add the force of friction. It doesn't quite work that way. So we notice that there, even though we have this extra 25 newtons of force of friction, we see that our tension only goes up by 10 newtons. Okay, so you really do have to work your way through all of the steps to figure out this tension on frictionless or on a frictioned system. Okay, hopefully that helps. I believe your worksheet only has a couple tension problems on there, much more elevator questions. We're going to continue with this tension and these types of systems again next week. Okay, so let's take a look at our elevator problems. All right. So we've talked about our tension problems. We've gone through a few examples, friction and frictionless. Now let's talk about elevators. Okay, now elevators, reason we kind of put these in, like, it does have, it's similar to tension. Let's just start it that way. Okay, now for this sheet and this sheet only, I want to simplify these calculations, ones that we can just do in our heads without calculators. And so I'm just going to say for this, gravity is 10 meters per second squared, and your mass is 50 kilograms. Okay, let's just make this nice and easy. All right, so part A, at rest. Okay, now we're talking about this as being at rest on the ground floor, but this is really at rest anywhere throughout this elevator's up and down trip. It is just like being on a ground surface. So at rest, okay, our F net equals the FG plus the, or minus the F net, or sorry, the normal force and the gravitational force cancel each other out. So for this one, for Q1, we want to know what is our weight. Well, weight, when we are not moving in an elevator, is just equal to Fg, which is equal to our mg. And so for this one, this is our 500 newtons. Okay. Question 2 for this situation is, what happens to this apple that we're standing here and we just drop it? Well, that'd be the same as being on the ground floor, and the apple falls with the acceleration equal to gravity of the 10 meters per second squared. Okay, so pretty normal to what we'd be seeing if we were just standing on a floor and looking at ourselves on a scale and trying to figure out that weight and what happens to the apple. Okay, well, that's the boring situation. Let's look at something a little bit more involved. Part B. We are accelerating up. At 2 meters per second squared. Okay, so for this one, this is where we really want to try and draw a free body diagram to kind of help and understand what's going on. So here is our elevator. We have our F applied going upwards. We have our FG going downwards. Okay, so in this case, F net equals, we're going to say FA minus FG. And this is also equal to our mass times acceleration. Okay. So we want to essentially look at, well, if we're accelerating upwards at 2 meters per second, we're looking for this applied force, because that applied force in this situation is also equal to our normal force, right? It's the force that's pushing us upwards, right? So the cable is pulling the car, but it's that car at bottom that's pushing us upwards. And so that's our normal force, essentially, right? And the normal force is what we experience as our weight. So in that first problem, we just said Fg equals our weight, because that is what we would see on the scale. Now for this situation, though, we want to find out what this F applied looks like. And our F applied is going to equal that F net plus Fg. Well, F net is mass times acceleration. So we have that 50 kilograms multiplied by our acceleration upwards of 2, plus we have our mass times gravity, like we said from the first one. So we're going to end up with 100 newtons plus 500 newtons gives us a 600 newton value that we're going to see on the scale. So if we're accelerating upwards, we see an increase in our weight because we are seeing an increase in the acceleration that we're experiencing. Okay, now that was for question 3. For question 4, what happens to that apple that we drop? Okay, well, we're standing here and we drop the apple. It's accelerating downwards already at the 10 meters per second squared, right? Gravity is pulling it downwards, but we also notice that the elevator is going upwards at 2 meters per second. So this apple, I'm just gonna draw as a circle in here, okay? It's gonna be falling with that force of gravity. And then the floor of the elevator is approaching this with that value of 2 meters per second. So inside the elevator, the apple appears to fall with a coupled acceleration here. So it's going down at 10, the floor is coming up at 2. So it appears that if you're in the elevator, that apple would fall at 12 meters per second squared. Okay, faster than either one of those two. We just kind of combine those because the apple is falling, the floor is coming up. Okay, so we see a greater acceleration on the apple inside that elevator. Okay. For part C, okay, we're saying constant velocity. Therefore, acceleration equals 0 meters per second squared. And so for this situation, this is just like being at rest on the ground floor. So for question 5 here, what is our weight? Our weight equals Fg equals 500 newtons. Okay, no extra acceleration. All we're experiencing is the force of gravity. And so when we look at question 6, what's happening to that apple? Same as question number 2. It is falling to the floor with an acceleration looking like 10 meters per second squared. Okay? So A and C are very same. If we're doing constant velocity or sitting at rest, we have no acceleration. There is no change in our net force. Okay. Some of the interesting ones now. Part D. We're still traveling upwards, but our acceleration is downwards, right? So accelerates up with A equal to negative 2 meters per second squared, right? We're slowing down as we're going into that upwards direction. Okay, so very similar here as we did in part B, right? We want to take a look at what's happening to our total system. We have our Fg, we have our Fa, we have our F net, or sorry, normal force, because we're slowing down in that upwards direction. Okay, our F net equals our m times our acceleration here, and it also equals our Fg minus our Fn. So our Fn in this situation then is going to be F net plus Fg. Right, move the Fn over, move the F net over, we get to these situations here, or sorry. There we go, that looks better. And so we are looking here in this situation that we have a 400 Newton situation. Okay. If we're accelerating upwards, we feel that floor pushing us further. If it's accelerating downwards or if it's slowing down, it kind of feels like it's falling out from underneath us and we have this less weight, right? So if our acceleration was 2 in the downwards direction, then we have this both going downwards here, right? So hopefully that helps out. And then for question 8, our apple, going upwards, or gravity is pulling it downwards. However, the floor is falling as well here, right? It's slowing down. So in this case, our acceleration from the apple is only going to be 8 meters per second squared. Okay. Now, when we're looking at part E, again, we've got a very similar situation to part D. This time we are accelerating down. And so it means we still have that negative direction, or it's the same as this gravity, right? And so we end up with that same situation, whether we're slowing down in the upwards direction or if the elevator is falling beneath us. We're still looking at these situations where our weight is going to be that 400 newtons, and our acceleration is still going to be 8 meters per second squared for that apple. Okay, it's not going to fall to the bottom of the floor as fast as if it was standing still because the floor is falling as well. All right, part F, we are in free fall. So in free fall, we are falling at the same speed as the elevator, right? And so in this case, the floor of the elevator is not putting any force on us, and so we actually have a 0 Newton, right? This is where we talk about weightlessness. If we're in free fall, we experience this weightlessness, okay? And so we would have 0 newtons for our weight, and the apple, from the perspective of being inside the elevator, would float, okay? I mean, we've seen airplanes, we've seen space, we've seen all these different situations where we are falling at the force of gravity, and it just looks like things float in those situations, and we experience that weightlessness in those situations. Okay, hopefully that helps with those tension problems and elevator problems. Take a look at those. Hopefully you understand what's going on. If not, make sure you post those questions in Teams, and I will get around to those for our office hour next week. All right, be safe, stay healthy, folks.